Hi guys. Today we're going to transition away from absolute value and look at just functions in general again. Today is another day that is something that is going to come back kind of over and over and over again throughout the year. So we're going to look at some operations, we're going to look at some notation stuff, and then we're also going to look at inverses. Inverses is going to be really important also this year. It's going to come back, like I said, several times throughout the year and in your future math classes as well. So we're going to start with kind of some pretty basic stuff, really just reviewing some operations and understanding notation. So understanding notation, if you have multiple functions, you can add them, subtract them, multiply them, divide them, which you probably know. We just want to make sure you're familiar with your notation. So if you see f plus g of x, we can write that as f of x plus g of x. We can separate it in that way. So f plus g of x is really just taking these two functions and adding them together. And when we add those functions, we combine like terms. So I'd end up with x squared plus 1/3 x. Let's make sure we know how to add fractions. Again, I know you guys probably have a calculator in front of you, but we need to be able to do this without a calculator very easily. So especially things like this, guys, you got to avoid the calculator as much as possible. If you want to use it to check, you can. I mean, if it's there, but again, you're going to be hurting yourself if you're going to be using a calculator for a lot of this. So we need a common denominator. So this would be rewritten as 25 over 5. So this would become negative 27 over 5. All right, moving on to subtraction. Same idea. Actually, though, this is probably one of the most frequently missed ones. And it's not because you write the wrong thing. It's because you forget I'm doing the f of x function minus the g of x function. But I cannot just write minus x squared minus 5. That's not what I'm doing. Okay, I'm subtracting this entire function. I need to put those parentheses there because you're subtracting the entire function. Guys, that gets missed so much. So be careful with that. Make sure you pay attention, subtract the entire function, distribute that negative. At that point, again, it's pretty simple. At that point, we're just going to combine like terms. So I end up with, I'm out of space, I'll write it up here. I've got negative x squared plus 1/3 x. I get my common denominator again, and I end up with 23 over 5. All right, f times g of x, we're multiplying these two functions together. So 1/3 x minus 2/5 times x squared minus 5. So we're going to FOIL this out. So 1/3 x times x squared would be 1/3 x cubed minus 5/3 x minus 2/5 x squared plus 10 over 5, which is just 2. Then I'm going to go ahead and rewrite this in what's called standard form. Standard form is really just your exponents basically are going from biggest to smallest. So I'm going to rewrite this as 1/3 x cubed minus 2/5 x squared minus 5/3 x plus 2. All right, now whenever we're doing these, with operations, sometimes it's not going to be necessarily of x. It may be of a number. So this is f of f divided by g of 2. So we're going to take the f of x function divided by the g of x function, but we're also going to evaluate it when x is 2. So I would just take, at the top, I would do 1/3 times 2 minus 2/5 divided by 2 squared minus 5. Evaluate it from there, so that's 2/3 minus 2/5. Get your common denominator, so that's going to be 10 over 15 and 6 over 15, which leaves me with 4 over 15. And then at the bottom, I've got 4 minus 5, which is negative 1. So 4 over 15 divided by negative 1 is really just going to be a negative 4 over 15. All right, so again, this isn't really an operation, but again, this is just some notation, getting used to seeing it, where we're evaluating the f function, where our x is being replaced with x plus h. So I would rewrite this function as 1/3 x plus h minus 2/5. I can go ahead and distribute and make that 1/3 x plus 1/3 h minus 2/5. All right, then look at the next one. Same idea, f of x plus h minus f of x. So I've got 1/3 x plus 1/3 h minus 2/5, because that's what I just did. then I am subtracting the entire f of x function. I'm putting it in parentheses. So that gives me 1/3 x plus 1/3 h minus 2/5 minus 1/3 x plus 2/5. And let's see what happens here then. All right, 1/3 x minus 1/3 x plus 2/5, negative 2/5. All I'm left with is 1/3 h. All right, so let's look at a few more. So another operation that we're going to use this year is something called composition. So composition sometimes gets confused with multiplication because it kind of looks like it a little bit. There's two different notations you can use for composition. One of them, you'll see this open circle here. One of them, you'll see kind of a function inside of another function. We're probably going to use this one more often, but it is still good to know that that little open circle does in fact mean composition. The way we read this is g of f of x. So this would be g of f of x. So what this means, the way it works, basically you take the inside function and you replace that in the other function. So let's look at an example with a number first. It's a little bit easier with a value. Start with the inside most thing, g of 3. So I'm going to evaluate g of 3. Take 3, plug it in for x. So that's 3 times 3 squared, that's 27. So g of 3 is 27, so this now becomes f of 27. F of 27 means take 27, plug it into the f of x equation. 27 plus 4 is 31. So as long as you can recognize the notation, it's not that bad. All right, again, starting at the inside, f of negative 2. Well, f of negative 2, replace x in the f of x function with negative 2, and I get 2. So g of 2. Now I replace 2 in the g of x function. So 3 times 2 squared, 3 times 4 is 12. All right, now let's go to C. Again, start with the inside. If you feel comfortable, guys, pause the video, try this one and the next one on your own. All right, g of 9. So evaluate. So I've got 3 times 81, which should be 243. Take 243, plug it into the f of x equation, and I get 247. Whoops. All right, next one. F of negative 5, start with the inside equation. So f of negative 5 is going to be a negative 1. G of negative 1, a negative 1 squared is a positive 1. Positive 1 times 3 is 3. So now we'll look at it with an equation. Okay, so f of g of x. That means the g of x function replaces x in the f of x function. So I'm going to replace x with 3x squared plus 2. If you want to write it out this way, it may be easier for you to see. This is f of 3x squared. Okay, we're replacing the x in the f of x function with 3x squared. So that becomes 3x squared plus 4. All right, same thing looking at my next one. G of f of x. So now this time, the f of x function is replacing x in the g of x function. Okay, we're doing g of x plus 4. So that means I'm doing 3 times x plus 4 squared. And let's go ahead and FOIL this out just for practice because, again, we talk about things that are frequently missed. This is frequently missed. You guys got to be really careful with this because a lot of times you guys will be going really quick and you'll say, hey, I'm squaring this. This is x squared plus 16. That is not x squared plus 16, okay? We're going to do this a lot this year. If you have a binomial squared, you have to remember this is x plus 4 times x plus 4. If you actually FOIL this out, you're not going to get x squared plus 16 because you have this middle term you have to worry about. So what I use is a little trick called square double square. Basically, you square the first term, you multiply and double, and you square the last term. And that's how you can multiply out that binomial. So it's square, double, and square. Again, if you want, just write it and FOIL it out. Okay, that's x times x is x squared, 4x 4x, 16. All right, then all that's multiplied by 3, distribute that 3, and then we're done. All right, so then from here, we're going to look at composition operations just a different way. We're going to look at it from a table. All right, so same concept, a little bit less math here, just making sure we understand what this notation means. So f plus g of 1, remember that means f of 1 plus g of 1. So look at my table. F of 1 is 3. G of 1 is 4. 3 plus 4 is 7. So pretty easy math, again, just getting used to that notation. F minus g of 3. So f of 3 minus g of 3. So 0 minus 6, negative 6. F times g of 2. So let's look at f of 2 is 2. G of 2 is negative 3. 2 times negative 3 is negative 6. Again, we're getting these from our table. All right, now we're going to look at composition. Okay, so starting on the inside, f of 3. So on my table, f of 3 is 0. Now I have a new question, g of 0. G of 0 is 7. All right, again, this is composition. This is that other notation. You may not see it that often, but you could see it potentially, so it's still good to know. So this means f of g of 1. So g of 1 is 4. So now I'm evaluating f of 4, and f of 4 is 2. All right, again, if you feel comfortable, pause the video. You can try these next couple on your own. All right, starting on the inside, f of 1. All right, f of 1 is 3. So f of 3 is 0. F of g of 4. So g of 4 is 0. F of 0 is 5. And then finally, g of 4 is 0. G of 0 is 7. All right, so what we're going to do now is we're going to take composition again, but we're going to actually work backwards. And what we're going to do is we're given a function, and we're going to kind of try and break it apart and see, hey, how could we write this as one function and another function and the composition of them? Now, this is going to be a little bit weird for now because you guys aren't super used to some of these parent functions, but this is a really good strategy that you guys will see kind of going forward back in your calculus classes later. So what we're going to look for is something kind of common between these functions. So what I notice here in this first one, I got a 2x minus 7 and a 2x minus 7. So what I'm going to do is that 2x minus 7 is going to be my x. So this is going to be 3 to the x plus x. So that we're going to call our f of x function. Well, what's replaced that is 2x minus 7. So what that means then is I could rewrite this h of x is the composition of those two functions. So we need to figure out, is this f of g of x or is this g of f of x? Well, since the g of x is replacing that x, this would be f of g of x. All right, now let's look at the next one. Again, kind of look for something that's common. Well, I've got this x minus 2 here. So I'm going to let the x minus 2 be replaced with an x. So I'm going to do f of x is the square root of x over x squared minus 3. What replaced the x was x minus 2, which means as a composition, since g of x replaced the x in the f of x function, then I can rewrite this as f of g of x. And again, these will get easier as you get used to seeing more of these parent functions. But for now, we really just want to kind of introduce it to kind of get you guys used to what this looks like. All right, so now we're going to transition to the other part of today, which is inverses. Inverses are really pretty simple, but they're really important. They're going to come up a lot this year and a lot in your future classes. And you actually have already done inverses before. You did inverses back in geometry. So you may have remembered whenever you had something like sine x equals 2/3. The way that you solved that is you rewrote it as sine with a little -1 of 2/3 equals x. And that's what you plugged into your calculator. That was called sine inverse, okay? It was an inverse operation. What's important to notice, what gets missed a lot, an inverse is not a reciprocal, okay? An inverse is a different operation where you are changing x and y. A reciprocal is like when you flip a fraction. So a lot of people think inverse, they flip up and down. That's what this says right here, okay? That's your notation for inverse. An inverse is not a reciprocal. Again, a lot of times people might think that is the notation. It's this little -1 exponent. Sometimes people think, well, if you raise something to a negative exponent, it flips a fraction. You're not raising the function to the negative first power. Okay, that's just your notation for inverse. It is not a reciprocal. The way we find an inverse, pretty simple. We switch x and y, and we solve for y. So let's go ahead and find the inverse here. So x equals 2y plus 4. So I'm going to write this with the right notation. F inverse of x is equal to 1/2 x minus 2. Now I'm going to go ahead and graph both these lines so you can see another property. So here's our inverse. And then I'll graph the original, which was 2x plus 4. So what's true about inverses is that they are reflections over the line y equals x. So if I were to take that graph and flip it over y equals x, that's what I would get. What's also true, again, we talked about switching x and y's to solve it. That's true for all the points on this graph. So let's take a point in this graph. On the original, I've got 0, 4. On the inverse, I have 4, 0. I have -2, 0 on the original. I have 0, -2. Both go through -4, -4 because switch x and y, it's the same point. All right, -3, -1 on the original. Then I've got -1, I kind of missed it a little bit. That's because it's not -3, -1, it's -3, -2. Can't read my handwriting. And on the original, it is -2, -3. So again, all those x and y's for every single coordinate are also switched. All right, so now let's look at some things with domain and range when it comes to inverses. All right, so let's go ahead and sketch the inverse of this graph. So like we said, we switch x and y. We can do that for the coordinates. So this point is -3, 0. So when I flip it, it's 0, -3. This point up here is 0, 3. So on the new graph, that becomes 3, 0. And then the original point that was 3, 0, switch x and y, it becomes 0, 3. So this is my inverse. So the first thing we're going to answer, is the inverse a function? Well, no. It's not that it can't be, but in this case it's not. And we'll talk about why here in a little bit. Now let's talk about domain and range. All right, let's do the domain of the original function. So here's my original, if you don't remember. So that is from -3 to 3 with brackets. Range, bottom to top, 0 to 3. Well, now let's look at the domain and range of the inverse. Domain, left to right, 0 to 3. Range, bottom to top, -3 to 3. So you may notice something. Those look pretty similar. They're just flipped. And again, think about it. That makes sense, right? If we're switching x and y, and domain is the x's, and range is the y's, well, then the domain of the original is the range of the inverse. The range of the original is the domain of the inverse. This is going to come back later on this year when we do some of our graphs. All right, if you feel comfortable, pause the video, try the next one on your own. All right, so again, we're going to just flip our x and y's. So this graph goes through 0, 5, so I'm going to go through 5, 0. This graph goes through 1, 4, so I'm going to go through 4, 1. This graph also goes through 9, 2, so I'm going to go through 2, 9. And we're just going to assume that these graphs have arrows on them. So is the inverse a function? In this case, it is. All right, let's do domain. Domain of the original was from 0 to infinity. Range of the original, be careful, again, bottom to top. The lowest y value of the original was negative infinity. The highest y value was 5. Domain of the inverse, left to right, negative infinity to 5. Bottom to top, 0 to infinity. And again, you'll notice they're basically flipped from each other. Now, the reason one of these had an inverse that was a function and one of them doesn't. We're going to talk about this again a little bit more later on, but what this does is this passes something called the horizontal line test. So you know how we use the vertical line test to determine if something is a function? Well, the horizontal line test will determine if that function's inverse is a function. So if it does, it has a special term called one-to-one, but let's start with like the original. That red graph does not pass the horizontal line test. If you draw a horizontal line, you touch 2 points. That means that the inverse of that is not a function. But looking at B, that graph does pass the horizontal line test. I can draw a horizontal line anywhere on that original graph, and it does not touch more than 1 point. So the inverse of that graph is a function. All right, so the last thing we're going to do is we're going to combine. The reason we have these on the same day is because composition is actually really helpful for determining if functions are inverses. So the way we actually prove this. Now, I know a lot of times what people want to do is they want to just say, hey, I solved for the inverse. I'm going to flip x and y, and I'm going to get this as an answer if it's true. But that's not really how we prove it. Okay? The way that we can prove it is by using composition. So what we do is we do both f of g of x and g of f of x. So I'm going to start with f of g of x. Remember, that means the g of x function replaces x in the f of x function. So this would be 3 times 1/3 x plus 1/3 minus 1. So that gives me x plus 1 minus 1, which gives me x. And that's what I want. But I can't just stop there. I also have to do g of f of x. We have to do it both ways in order to prove that these graphs are actually inverses of each other. So for g of f of x, we'll take the f of x function and plug it into x in the g of x function. So this would be 1/3, 3x minus 1, plus 1/3. So then we can go ahead and distribute. 1/3 times 3 is just 1x. Minus 1/3 plus 1/3 gives me just x. So because f of g of x and g of f of x both equal x, then those two functions are inverses of each other.